Hello and welcome. My name is Ameer Abbas. I'm a product manager at Google. I focus on application and platform modernization. Last year, I delivered a presentation with an eerily similar topic to this one. It was called Building Globally Scalable Applications with Istio and Anthos Service Mesh. So you're probably wondering, why am I doing the same presentation again? Well, not quite. I thought this year I would take some of the foundations and principles we talked about last year and put them into practice, and I can show you some of the practical applications of delivering modern applications. So let's get started. Let's talk about a service. Everything revolves around a service. We build our teams, our organizations, our engineering, our product teams to deliver beautiful, scalable, resilient services to our customers. Every service needs a few things. For instance, a service needs to be resilient, it needs to be scalable, it needs to be secure, and most importantly, it needs to be manageable. And what we mean by that is, by resiliency, I mean that we need to be able to weather the storms against any infrastructure, human, or machine error. Scalability is pretty self-explanatory. We need to be able to run our services on many computers, maybe in many Kubernetes clusters, in a lot of different zones, in many regions. For security, we want to encrypt all traffic, all communication between services, and we want to be able to have the tools to implement policy and enforce policy to and from every single service. And for manageability, there's a lot of things that fall under that umbrella. For instance, what do we want to observe? How do we want to measure the signals? How do we deliver traffic to the right instance of a service? And how do we reliably roll out new versions of a service and keep innovating and manage the configuration that revolves around a service? All of that falls under manageability. So let's recap. Last year, we talked about running services in a single cluster. Here we have a service called frontend running in the frontend namespace with a pod, and it's running in a single cluster. And everything is fine and dandy until that cluster goes down. And as soon as that cluster goes down, that service and any other service that's running in that cluster also goes down with it. So we've kind of broken that first tenet of resiliency, which is that we can't even weather the storms against infrastructure failures. So what do? Well, we run our services in more than one cluster. So we run something called distributed services. A distributed service is just a Kubernetes service that runs on multiple clusters. From an outsider's perspective, it's the same logical service. I don't need to know that it's running on multiple clusters. So here I have the same service front end running on 4 clusters. On the left-hand side, I have 2 clusters in region 1 in 2 different zones. And on the right-hand side, I have 2 clusters in region 2 in 2 different zones. So you can see that not only do I have cluster resiliency, I have zonal redundancy and regional redundancy. And what that means is if my cluster goes down, I still haven't lost my service. I have 3 other clusters that can serve traffic for that service. I can lose an entire region and I have not lost that service. I can lose multiple clusters in multiple regions. As long as that last cluster has enough capacity to serve traffic for that particular service, I'm good to go. So you can already see the effects of scalability and resiliency when you run distributed services. Well, with distributed services comes a few considerations that you may not consider in a single cluster life. For example, service discovery and traffic routing. In a single cluster, service discovery and traffic routing are kind of automatic. When you drop a service into a cluster, it gets automatically discovered. Other services can get to it. Routing just works. So how do we do that in a distributed service environment? Here we have 2 distributed services. What if the front-end service wants to talk to the cart service? How does the front-end service know which pods are healthy for the cart service, which pods to get to, and how to route to those pods? So this is kind of the east-west traffic problem. Next is Ingress. Again, in a single cluster environment, we have an Ingress object. We deploy the Ingress object, and we can get traffic from outside of the cluster to our service, no problem. Well, how do we do that in a multi-cluster environment? How do we do multi-cluster ingress? So this is the multi-cluster ingress, or the north-south problem. And then when we bring location into the mix, things get a little bit more complicated. Here we have service running on 2 different regions. Let's say region 1 is in Europe, and region 2 is in Asia. So the users that are in Europe or closer to region 1, we want to deliver their traffic to an instance of a service that's closer to them, so in Europe. And likewise, for the users that are in Asia, we want to deliver their traffic to an instance of a service that's running in Asia. Only when something goes wrong, for example, let's say everything in the Europe region is down, now we want to send the traffic from European users over to the Asia users. So how do we manage all of that? And then lastly, telemetry. Again, in a single cluster environment, we have implementations and tools where we can measure logging and tracing and metrics for every single service. How do we do that in a distributed service? Which signals to measure? How do we know if a service is healthy? What to alert on? So all of those things we're going to talk about, and we're going to use Anthos Service Mesh to solve some of these things. So let's go to the demo. Let's get oriented to the environment. Here I have a Google Cloud project with 4 GKE clusters running. GKE 1 and 2 are running in region US West 2. GKE 3 and 4 are running in region US Central 1. So it's the same 4 cluster model that we just saw. Let's look at the workloads page. I've deployed a few sample applications, and one of them is the famous online boutique retail application that consists of 13 services. I've deployed each service in their own namespace, and you can see by the workloads that each service is deployed as a distributed service. So add is running on all 4 clusters, cart is running on all 4 clusters, shop frontend, which is how you access the application, is also running on all 4 clusters. Let's take a closer look at one of these deployments. So we're going to look at shop frontend running in GKE 1. And I'm going to look at just the pods for that particular one. You can see that this pod is running 2 containers. One is the shop front-end container, that's your actual application container. And then the other one is the ASM sidecar proxy called the Istio proxy. Now this proxy governs the flow of traffic to and from this particular container. And if we look at the configuration of this proxy, we can see what version of ASM we're running. So in this case, we're running 1.10.4, which also correlates to the Istio version. We can also see that we're using the Google Managed Mesh CA as our certificate authority. We can also see that our trust domain is the workload identity for the project, and I'm using the same trust domain for all 4 clusters, and that's how services can talk and trust each other across clusters. What we want to do is we want to look at, from this Istio proxy's perspective, how does it view other services? Let's quickly jump into the terminal, and I'm going to go ahead into my GKE 1 cluster. Let's look at the pods. So kube control get pods. This is the same pod that we were just looking at in the console. We're going to use the istio-ctl CLI command, and I just want to look at the proxy config, and I just want to look at the endpoints configuration in the proxy config for this particular pod. And instead of dumping out the entire config, I'm just going to grep it for one of the services, which is the cart service. And here you can see that from the perspective of this shop frontend pod, it sees that there are 4 endpoints out there that it can access when it accesses the cart service. These IP addresses point to the pod IP addresses of the 4 endpoints. Let's look at the pods. So first thing I'm going to do is look at the pods in the GKE 1 cluster that's running in shop cart namespace. So shop cart namespace is where the cart service is running. And you can see that in GKE 1 cluster, I only have 1 pod running with the IP address of 10.0.2.11, which is the same IP address that you see up here, which means that the other 3 IP addresses correspond to pods running in the other 3 clusters. And we can quickly verify that by just picking one other cluster, for example, GKE 4. And again, in GKE 4, we're also just running 1 cart pod with an IP address of 10.8.2.143, which is the IP address here. So the ASM control plane goes out and discovers the endpoints for every single service and configures every single Istio proxy with those endpoints. And that's how every single service and every single pod knows how to get to every other service. So that's how the service discovery piece is working. But we also want to make sure that the traffic routing east-west is working. So for example, the front-end service can talk to the cart service. So in order to demo that, it's best done visually through a dashboard. So here I have created a custom dashboard for the cart service. And this dashboard here on the left-hand side, I'm looking at the request rates, and I've grouped them by location. So I want to see who is accessing the cart service from which location. And from the legend here, you can see that I'm receiving requests to all 4 pods. And further, I can group this by, let's say, a source service, source canonical service. And here you can see that there are only 2 services accessing shop cart. One is shop frontend, the other one is checkout, and both services are accessing all 4 locations. And you can see that I have a load generator that's running, that's showing me that the traffic routing is working. So in GKE, every pod can talk to every other pod if you have deployed GKE in VPC native mode, as long as you have the appropriate firewall rules. So now east-west traffic is working. Next, let's take a look at north-south traffic and how Ingress works. So for that, let's go back to our clusters page. And you'll notice that I have this 5th cluster called the Ingress config cluster. This is the cluster on how I configured multi-cluster Ingress. Let's take a closer look at this cluster. So I'm going to go back into my terminal. I'm going to change my context to the Ingress config cluster and change my namespace to Istio system. Inside of the Istio system namespace, I have two resources. I have a multi-cluster ingress resource, and I also have a multi-cluster service resource. And I have multiple applications, and that's why you see a couple of these. So the multi-cluster ingress resource corresponds to a ingress resource, and a multi-cluster service resource corresponds to a service resource, just like you would normally configure an ingress and a service. So let's take a closer look at each of these. So I'm going to look at the multi-cluster ingress resource first for the online boutique. And you can see that the multi-cluster ingress resource looks a lot like an ingress resource. So I have a rule with a host. So here's the host of how I'm going to access this application. And it points back to a service. But in this case, instead of pointing back to a Kubernetes service, it's pointing back to a multi-cluster service on port 80. And then if we look at the multi-cluster service resource that corresponds to this, again, it looks a lot like a Kubernetes service resource. So if we look at especially the spec of that particular resource, you can see that it has a service name, a port, and then most importantly, it has this selector. And what it's selecting is the Istio Ingress gateway as the backend service. The only difference here is these cluster selectors, and in this particular case, I've selected all 4 clusters. So essentially what I've created is the multi-cluster ingress. You can think of it as the front end that points back to 4 different backend services that matches this selector, which is the Istio Ingress Gateway selector. And what that creates, if we go back to the console, and I'm going to go to Network Services Load Balancing, is a front end with 4 backends. So here, if we just look at these top 2, as a matter of fact, if we look at the second load balancer, which is the online boutique Istio MCI, that got created when we created that MCI resource. And it gave me a front end. We'll talk about the certificate here shortly. But more importantly, we have created 4 backends, and these 4 backends are pointing to the Istio Ingress Gateway services running on all 4 clusters. And we can verify that by looking at the zone, and you can see that all 4 zones are covered. And if we click on any of these endpoints, you can see the actual pod IP addresses, and then they are healthy. If we go back to this certificate, I've created a Google Managed certificate for a DNS name. So remember, in the multi-cluster ingress, we had a host field that pointed to this DNS name. And so in order to access this service, I can just simply copy this, open a new tab, paste it, and you can see that we can access our online boutique application, and we can navigate around this application. So here I'm looking at product description, adding it to the cart. Here I'm looking at the cart service. I can place the order, which invokes the checkout service, and you can see all the functions are working for that particular application. The way the actual traffic flow is working is when I access this URL, if I scroll back, I'm going to this front end IP address. From this front end, traffic is being routed to one or more of these Istio Ingress Gateway backends, and then the Istio Ingress Gateway backend routes the traffic to the shop front end. So the next thing is the implication of locations. So remember, I have Istio Ingress Gateway running in 2 different regions in 4 different clusters. I also have the shop front end running in both of these regions in all 4 clusters. So what I want is, if I'm closer to US West 2 region, I want to go to the US West 2 Istio Ingress Gateway, and then eventually also to the US West 2 shop front ends. So let's take a look at how that is configured. I'm going to go back into Kubernetes workloads, and I have a load generator running for the online boutique. And you notice that my load generator is only running in the West 2 regions. And this is so I can show you locality load balancing. I also have locality load balancing configured, but only for the shop front end application. And the reason is just for this demo purposes. So let's go to the console. Let's go to one of the clusters, GKE1, for example, and I'm going to show you the destination rule that's running for the shop front end. You can configure locality load balancing mesh wide, but I prefer to configure it on a per service level. So here I've configured it just for the shop front end. And the destination rule determines how the traffic is routed once the routing decision is made. And this is where you configure locality load balancing. So here in the load balancer section, you can see that I have locality load balancing enabled. I also have a failover setting, which says go from US West 2 region to US Central 1, since I'm looking at the GKE1 configuration. And then I also have this outlier detection, which determines when a failover or a failure occurs. This is a very aggressive rule just for the sake of the demo. Essentially, I'm saying is for in every second, even if I have a single error, consider that an outage and eject that particular deployment for a minute. And so you can see that just with the addition of these 5-10 lines, I've created locality load balancing. And I have the same exact destination rules for all 4 clusters for the front-end service. So in order to prove that that is actually working, remember that my load generator is only running in US West 2. So what I should expect is only the West front end to be receiving traffic, because nobody else is really accessing this particular application. So the best way to do that is let's look at the charts. So here I have a custom dashboard that I've created for shop front end, very similar to the one that we were looking at for cart earlier. Again, we're looking at the request rates, and I've grouped those by locations. So I have the 4 locations, so US West 2 AB and Central 1 AB, but you can see that I'm only receiving traffic to the shop front end only in the West regions and not in the Central regions, even though I have pods running in the Central region. That means locality load balancing is working, and you can configure the same locality load balancing for every single service. So in a sunny day scenario, that works great. Everything will go to its closest endpoint. But what happens when there is a failure? So my load generator is running in the West region. What happens if the West region is down? I should expect that load generator to start sending traffic to the Central region because I've configured the failover rule as such. So let's do that. In order to simulate that, all I'm going to do is scale the replicas for the shop front end in the West region down to 0. So let's go to the console, and I'm going to run the scale command. I'm just going to fix this spelling error. So all I'm doing is scaling the shop front end deployment replicas down to 0 in GKE 1, as well as in GKE 2. These are my 2 US West locations. What that's going to do is render a failover from US West 2 region to US Central 1. So we'll wait a few minutes and see how the charts do. A few minutes have passed, and now you can see that all of the traffic is routed to the central servers. So I have not changed the load generator's location. It's still running in US West, but because of the failover from US West, we're now going to Central 1. The chart to the right is also showing us error rates by location, and you can see that for the same time that the failover occurred, we did not experience any errors, so it was a seamless failover. And we expect this to kind of go back when we change the replicas back to 1. So let's quickly do that. So we go back to the console. All I'm going to do is rerun that command, but this time change the replica to 1 for GKE2 and for GKE1. We'll wait a few minutes. And now we see that the traffic has gone back to the US West 2 clusters and no more traffic going to the central clusters. So we're back to our sunny day state of locality load balancing. And again, we did not experience any errors throughout this changeover. So this technique is also useful if you want to perform some scheduled maintenance on a cluster. You can now manually and explicitly drain clusters by scaling just the replicas down for any cluster down to 0 and shifting traffic over to different clusters as long as there's capacity there. And then you can perform an upgrade or any kind of maintenance on those clusters. All right, the last thing we want to look at is observability and manageability of services. So for that, let's go back to the Cloud Console. And here we're going to go to Anthos Service Mesh. When you have Anthos Service Mesh deployed on one or more clusters, you will get this dashboard view. Now, this dashboard view gives you a table view and a topology view for all the Anthos enabled services. So here I have all of my services that are running in multiple clusters. So for example, shop front end is running on 4 clusters. I can look at which 4 clusters it's running on. This comes completely out of the box without you having to instrument anything in the application. If I click on shop front end, I can get further information about this service. So I can see inbound and outbound services that it's talking to. I can get the golden signals. I can look at the metrics for this particular service. These are canned dashboards, again, that come with every single service. So you get these dashboards out of the box. So you get requests per second, error rates, latency for the 3 different percentiles, the 50th, 95th, and 99th, as well as request size, response size, CPU memory, and disk for every single service without having to instrument anything. From here, you can also go to application logs. So I can just click on application logs and it will create the right filters for me. So I can just look at the application logs for the front end so I can see that, I have requests going in and out.
I can also look at traces from here. So I can just click on traces. So if I want to look at request trace, this is something you do have to configure in your application. I can look at the histogram of my requests coming in, and then I can click on as an individual request, and I can obviously look at that particular trace information. Again, all of this is part of the Anthos Service Mesh. Furthermore, I can go to health and I can create SLO. So here I've created an SLO for latency-based SLO for the front-end service. And if I open this up, and if I edit this SLO, I can just kind of show you how I created it. So the first thing is I picked latency as my metric. I can either choose availability or latency. I can hit continue. Here's the actual signal or the metric that I'm using, which is the response latencies. I can see the historical response latency, and based on that, I just picked a value. So here I could see that there are some spikes above 1500 milliseconds. So I just picked one for 1500 milliseconds. You give it the compliance period. So I'm picking calendar day, and I'm keeping my goal at 95%. So 95% of the time I want my latency to be 1500 milliseconds or below for that particular service. If I hit continue, it also gives me the JSON view of that particular SLO. So I can use the SLO API to create this if I'd like. And then I just create my SLO. So for every single service, you can do that, and I recommend you do that for every single service, and you can do that in your as part of your CI/CD pipeline. This is where you'll get your SLIs and your error budgets, as well as if you've configured any alerts. You can create alerts by just clicking on this. And you can measure how exactly your service is being experienced across the board. So we typically recommend at least creating 2 SLOs for every single service, one for availability and one for latency, so you can see whether your users are actually able to access your service and then what is their experience when they access that particular service. So that's the end of the demo. Let's go back to the presentation.
A few calls to action. First, hopefully it's very obvious, run distributed services. Never bet your services on your infrastructure. By running your service on more than one Kubernetes clusters, you've immediately gained the advantage of scale and resiliency. Second, monitor your distributed services. Golden Signals is a great place to start. Right? Somebody gave me this analogy that when you go to the doctor, they don't try to diagnose you for every single disease. Right? They look at your symptoms and then they figure out exactly what's wrong with you. So alert on symptoms, not on every single potential cause. In a distributed world, there are thousands and thousands of signals out there. And if you want to alert on every single time a CPU or a memory spikes, you're going to get overwhelmed. Lastly, use location as a benefit. I see 2 main benefits for location, especially if you're running multi-regional services. First is you can deliver your service closer to your user, right? And secondly, thinking about failure domains. So I think of failure domains in terms of concentric circles. For instance, a Kubernetes cluster is a failure domain. When a cluster goes down, it only takes down the services that are running on that cluster. A zone is a failure domain. If all the clusters in a zone or the zone itself goes down, then that zone cannot serve traffic. And a region is a failure domain. Thinking in those terms helps you kind of figure out how to do maintenance windows and scheduled operations on your infrastructure. If you want to build distributed services, you can go to this link, bit.ly/run-distributed services, or you can pause the video and scan this QR code that takes you to the same link. I thank you for your time and enjoy the rest of the conference.